Okay, so this is lecture 16 in our semester. So today we will talk about the IV characteristics of a PN junction. So I wanted to start from our previous slide, the last slide. So with the law of junction, we have a simplified problem. So basically we have to solve three different equations, Poisson equation and two continuity equation. However, by introducing some approximations, then now this problem can be really simplified as a just diffusion equation. Why we have a diffusion equation in this case here? This is the p-type region, and we assume that this region is quasi-neutral because we have almost no potential drop in this part. So now let's think about the case where this quasi-neutrality is not satisfied. So then what will happen? For this small or this p-type region, we have a certain amount of voltage difference, and you know that here we have a lot of hole its density is corresponding to acceptor density. So we have tons of holes there, and they are accelerated by this potential difference. Then it will generate a lot of current, so that cannot be supported by our other reasons like space charge reason. So we assume that the charge neutrality or quasi-neutrality is obeyed. So simply speaking, current conduction mechanism can be written as drift and diffusion. However, driving force for this drift mechanism is just the voltage difference between 2 points, or electric field is the driving force for this mechanism. So simply speaking, in a quasi-neutral region, we have to have only diffusion. So that's the reason why we can consider only one equation, electron continuity equation, because you know hole, in this case in this p-type region we don't care about hole, and in this case we consider only minority carrier electron. And how about Poisson equation? By solving the Poisson equation, we must calculate the electric field distribution. However, we just assume that quasi-neutrality is applied, so electric field is almost vanishing in this region. So that's the reason why, although in principle we have to solve three different equations, but we can be simplified into just a single equation without any drift term. So that is shown in this slide. So among three different equations, we must solve electron continuity equation in p-type region, and it can be written as this form. Yes, so this is quite a general form, and here we have net recombination and generation. Yes, in the p-type region, so we believe that the electric field is weak, so although we must consider drift and diffusion in general, but that is just written as simple diffusion term. So could you please go to this way. So here we have Jn, but drift term is just eliminated, neglected, and now we have Q dn, and once again gradient of electron density. That is the form for without the drift operation. However, this 1 over Q and Q are cancelled out each other, and here we have made another approximation. Of course, dn, diffusion constant of electron, can be a position dependent quantity. However, in this simple analysis, we just pull it out of this spatial derivation. So now we have dn, and it's a dn and second order derivation of our electron density. That's the reason why we have arrived at this form. So please regard this dn as a constant value. Then maybe you can ask me the question, is this really true to have a constant dn? Obviously not. So obviously we may have different values, but please understand, sometimes we are talking about behavior of electron density, and in many cases electron density does not change linearly. Sometimes it is exponentially changing. So small differences in this dn can be neglected from the exponential behavior of our electron density. Of course, yes, we are right. We must, in order to be really accurate, we have to consider also position dependency of diffusion constant. But anyway, right now we don't care about it. So this is the form here, and we must consider also net recombination term. So this is corresponding to net recombination. Whether that is net recombination or net generation really depends on the relative magnitude between NP and Ni square. Everybody understand, if there exists a relation between these two terms, then this is nothing but an indication of equilibrium status. So if we have a perfect balance between NP product and Ni square, yes. However, now think about two different cases. One case is our NP product is larger than Ni square, and the other case is our NP product is even smaller than Ni squared. Then please think about the situation. This one is more or less we have excessively more carriers, and in this case, this one typical example is it is really 0 and it is really 0. Then of course we have this condition. It means that this NP product is even smaller than Ni square, is the depletion. However, this is not the depletion usually found in the p-n junction at equilibrium, but even further severe depletion of our electron and holes. So now think about our case. We are now considering a forward biased diode. Then what will happen? Think about this one. When we come back to this point, please try to estimate the electron density and hole density. Hole density, that is quite close to accepted density, and if we have Ni square divided by Na, then this is corresponding to the zero applied bias case. However, following this law of junction, if we apply a positive forward bias to it, then instead of this term, now we have an additional factor corresponding to exponential V applied, of course normalized by summer voltage. So you know that this one is larger than 1, so you can expect yes, NP product is larger than square of Ni. So are you all with me? Simply speaking, if this is at equilibrium, then electron density would be just this number. However, since we are now considering slightly forward biased junction, electron density is increased. Minority electron carrier density is higher than its usual equilibrium value. So now we expect that NP product is higher than squared Ni, so it is nothing but net recombination will occur in this case. So now let's come back to our case. So in this case, okay, now we will have this net recombination. So electron density is assumed larger than in its equilibrium value. So we will have a positive this difference n minus np naught, and that will contribute to certain kind of recombination factor. So electrons are approaching to its equilibrium value when we solve this continuity equation. So that sounds really quite natural. However, please think about the case of a slightly different one. Like, for example, if we consider a reverse biased junction, then what will happen? If we have a reverse biased junction, then there is no guarantee that NP product is larger than Ni square. Actually, it is certain that NP product is smaller than Ni square. Then in this case, there is not sufficient numbers of our electrons and holes to be recombined. So there are two different mechanisms. So if we have electrons and holes in conduction band and valence band, they are recombined. This is one way of reaction, and another reaction is natural generation of electrons and holes. Yes, there is also another two different mechanisms. However, in this case, since we have not sufficient number of electrons and holes, so this net recombination never happens. Then remaining thing is only the generation of our electrons. Okay, so please come back to our previous lecture material. Then you will find that the recombination form and actually this is corresponding to this form. When we have a reverse bias junction, then we can clearly neglect this form, and only minus Ni square will give you certain constant value of carrier pair generation. Okay, but right now we are considering this form, and at steady state, of course, so now we are going to this part. At steady state, we assume that every quantity is time independent, so time derivative terms goes away. So simply speaking, well, yes, this is corresponding to this one that is shown here. Yes, this is the equation we will get, and we just define a quantity called as electron diffusion length, which is defined as, there is nothing special, we just defined in this way. So minority, carrier lifetime, and diffusion constant of our minority carrier, that is corresponding to this diffusion length. Okay. So typically this diffusion length is orders of micrometer, several micrometers. So a few micrometer or a few 10 micrometers in usual. So please think about the size of our PN junction nowadays. The junction is really short compared with this electron diffusion length or hole diffusion length. So although we will do some jobs related with long diode equation, however, please keep in mind that in reality, all of your diode found in VLSI device should be regarded as actually a short diode. Here short means that the size of your n-type region or p-type region is compared with the electron diffusion length or hole diffusion length. If the size of your quasi-neutral region is shorter than this diffusion length, then you may say that for that part your device, your diode is short, or on the other hand, low. Okay. Then now let's go to our diffusion equation. So in this slide, I will assume that the boundary corresponding to the anode is located far away from our junction point. It means that here we have this configuration, and now we have additional excessive carriers by applying the forward bias. After that, it will be anyhow reduced to its equilibrium value. However, distance between this starting point of our quasi-neutral region and ending point of our quasi-neutral region terminated by this anode contact is infinitely long. So, of course, this is not the case, but we will first assume this kind of simplified behavior. Okay, so following our previous notation, so starting point of our quasi-neutral region is written as x sub p, and this is located, anode contact is located at far away from this point. Then this one just shows that nothing but low of junction, and this second condition is obtained from our anode contact, and this means that we have a perfectly ideal ohmic contact. Okay, then we must solve this diffusion equation. Then the answer is quite simple. This one support the form of like this. This one. This form is supported by our solution exponential x over ln, or exponential minus x over ln. These two basis functions are available as a fundamental solution of this equation. How can you check it? Please just insert one of them into your diffusion equation. Then you will check that these are solutions. And of course, here we have different signs in its argument. Here we have a positive x, and here we have a negative x. And in this configuration, of course, which one is physically reasonable and which one is unreasonable? Of course, this one is reasonable because this function describes an exponentially decaying function. Excessive excessive electrons that comes into this very beginning point of your p-type quasi-neutral region, and there are a lot of recombination. So we expect that the reduction of or decrease of your electron density. Therefore, this exponentially decaying function is suitable for your description. If we take the other one, exponential positive x, it means that our electron density is now increasing. So it never match this kind of boundary condition. So therefore we have to reject this one. So that's the reason why for this case we can have this diminishing or exponentially decaying function. Wow. And our textbook, Professor Tower's book, consider a finite thickness of the quasi-neutral region. So in the next slide I just summarize the result. Okay. If we consider finite thickness WP Yes, then how can we proceed? Instead of xp, because xp always makes some offset here, so here you can see that here always xp occurs. So instead of having a given number xp, we just set a new coordinate system in this problem. So let's say that x equals 0, that is corresponding to the starting point of your what, your quasi neutral region, and also define wp as not the entire length of your p-type region, p-type doped region, but this one wp is intentionally defined as length of only quasi neutral region. So simply speaking, depending on the bias, actually your WP can be modulated. For example, if you apply a negative bias, so reverse bias, then actually WP can be shortened. And if you apply forward bias, then since depletion is becoming narrower, so you will have a wider WP. But anyway, let's assume that you have this kind of a description. Then things gets more simpler by adopting this one, because our two boundaries is now no longer regarded as xp and infinity. Instead of that, we have introduced two boundaries, x equal to 0 and another one is x equal to wp. In these 2 points, we can assign the same values, the value obtained from what? Value obtained from our law of junction, and another one obtained from ideal ohmic contact. This is not that much different from previous one, and everybody also understand the available basis function still given as x over ln or exponential x ln, exponential minus x over ln or positive 1. So same problem, only with different boundary values. And you know, if we consider only this term, it never generates 0, because exponential function is always gives us a positive value, right? So if we have a very large argument into it, then maybe our exponential function will decay to 0 quite rapidly. However, still, if we say, is this really 0? Then actually not. So in order to match the real condition, yes, this condition, we have to have combination between this exponential function and another exponential function. Then how can we have this combination of these two? There can be some ways, and one way is hyperbolic sign, and another one is cosine, hyperbolic cosine. So among them, in this problem, we have sine hyperbolic. Hyperbolic sine is the one, and you can easily derive the expression shown here. Simply speaking, actually I hope that most of you, this is not that difficult. However, I wanted to make it as detailed as possible. So let me just explain a little bit further. So from this first boundary condition, if we consider n minus n equilibrium condition, then at x equal to 0, we will have np naught and exponential something minus 1. That will be the boundary condition. And if we consider the position corresponding to wp, then it will become just number 0. Yes, so therefore in order to match these two boundary values, then we have to introduce hyperbolic sine or hyperbolic cosine, but in this case hyperbolic sine is the right one, and you will have this form. Please do your exercise to solve this problem. Okay, then hyperbolic functions are summarized here, and this is, if I remember correctly, this is corresponding to hyperbolic sine, and this one is corresponding to cosine, and you know, here we have one curve that is corresponding to hyperbolic tangent. This is nothing but, this hyperbolic tangent is just sine hyperbolic over cosine hyperbolic. You know it. And typical point is, if we go to very large input argument, if x goes to infinity, then this tangent function, hyperbolic tangent function, approach to number 1. Okay, so are you with me? Yes, this is corresponding to number 1. Of course, if we go to the negative value, then this one is corresponding to -1. But right now we will consider only positive input argument. Okay. Then from this one we can calculate electron current density. Electron current density is Jn, and of course, in order to calculate Jn, in general, you have to consider also drift term. But fortunately, we have already neglected the drift term, so we can approximate it this way. Current density is nothing but just Q dn times dn over dx. And do we know now dn over dx everywhere in this quasi-neutral region? The answer is yes, because we have just derived the form for our electron density, minority carrier density inside the quasi-neutral region. So what we have to do is just to take the derivative once. Then with respect to x, then you can see that this one is constant, so when you take derivation, so it goes away, and this one is also constant, and this one is a function of applied voltage, but it is not a function of the position. Where can you find the function of a position? You can find only in it. So when you consider this one, so simply speaking, although it has so many ugly terms in front of it, basically the action we have to do is just this one, Wp minus x Wn, and you know, just like sine and cosine, hyperbolic sine and hyperbolic cosine gives also the same relation. If we take derivative, then it becomes nothing but just Wp over x Ln. Well, however, the input argument should be also derived once again, so we will have minus 1 over diffusion length, so that will be the expression. So when we just insert this result into our diffusion current term, then eventually you will get this seemingly quite complicated, but please don't be fooled by this complicated form. Where do we have bias dependence? Bias dependence is only shown in this part. If you apply positive applied bias, then your current density will be exponentially increasing, and there is a certain coefficient, and position dependency is only considered in this way. So we have once again exponentially decaying function of current density. So I'm not kidding. This one just to describe the current density exponentially decaying. Well, think about this one. Yes, this is a position and this is our electron density. What we are assuming is this is the behavior of our electron density. Therefore, if we take the derivative or slope of a normal line, then how does it look like? Yes, in this case, you will have a very steep line. Here you have a moderate line, and eventually your slope would be very small. So simply speaking, so I think that students should be confused by this fact. I mean that current density Jn is not a constant any longer. It is dependent on position. Well, at the beginning of our quasi-neutralism, we have quite high electron current density. But if we go to the anode current, anode contact, then what will be the electron current? According to this expression, it means that there is almost no electron current density. Although we have so large electric field here, so high electron current density, but that diminishes in between this p-type region and nothing left. Obviously, that should sound strange because everybody in this classroom believe that current should be conserved. At every position, current should be a constant. I mean that think about a load and tunnel. Yes, we have no idea about what happens inside this tunnel, but a car comes in, then after some minutes later, we expect that the same car should escape from the tunnel. If that doesn't happen, then what happened? Something, car crash or certain accident happens in here. It means that we just push our electrons. Electrons are injected from n-type region into p-type region. Oh, we have so many excessive electrons. But when we measure electron here, then unfortunately there is no flux, no electron current due to these electrons. Then when you just consider current density due to electron, there is no current conservation. That sounds quite weird. Okay? I will explain it right after this slide. And anyway, this is the form of our electron current density at any position in p-type region. However, typically we are interested with the beginning point of our quasi-neutral region. So we just insert x equal to 0 into this form. Yes, if we insert x equal to 0 here, then now this upper part just becomes cosine hyperbolic, and lower part we have sine hyperbolic, so they just become 1 over hyperbolic tangent. That is shown here. And you know, hyperbolic tangent goes to 1 when its input argument is so large. So let's come back once again. This is the hyperbolic functions, and for hyperbolic tangent, if we have a sufficiently large input argument, positive input argument, then it approaches to number 1. So simply speaking, when we have WP. So the length of a quasi-neutral region much longer than electron diffusion length, minority carriers diffusion length, than actually the current density at the beginning of a quasi-neutral region can be written as simply this form. Nothing but it is exponentially dependent on your applied voltage, and here we have certain coefficient. dn is diffusion constant, that is quite understandable, and only thing we have to care about is these two. This is equilibrium minority carrier density, and here we have ln, electrons diffusion length. So if we have, for example, if we have 10 to the 17 per cubic centimeter and 10 to the 20 per cubic centimeter as a acceptor density, then please try to estimate what's wrong. If we consider the equilibrium minority carrier density, then that will be in this case 10 to the 7, in this case 10 to the 0. So are you all with me? So therefore, if we have highly doped region, actually this value becomes very small. Or on the other hand, if we have a relatively lowly doped region, then actually this minority carrier density is somewhat higher than that of highly doped region. So we have more contribution to the current. So let's come back once again. We have a one-sided junction in many cases. In many cases we have one-sided junction, and you remember that actually when we consider diffusion width of entire device PN junction WD, then for highly doped region we have quite a short depletion region, and almost all of our depletion layer is supplied by relatively lowly doped region. That was the thing we have studied in solving Poisson equation, and today we now understand, even in the case of current conduction, the effect of highly conductive region is quite marginal. Only the contribution from our transport in relatively lowly doped region is important in estimating the carrier. So simply speaking, if we have n plus p junction, then most important current conduction mechanism is excessive electrons sent from this n plus region into p type region, and this electrons movement, that is most important one, because simply the hole injected into this n type region is so small, therefore they cannot contribute to the total current reasonably. Okay. So now we are now coming back to discussion about continuity of electron flux. As I told you before, in this setting, so inside our p-type quasi-neutral region, the electron flux shows some derivation. For example, let's think about this one. This is the flux of electrons at the beginning of our, this is the beginning point of our p-type region, and this is the ending point of our quasi-neutral region. Here we have certain amount of electron flux, because in this case we have many excessive electrons and their gradient shows some numbers. However, at this point we have almost no electron, excessive electron, and their gradient becomes 0. So almost no electron flux at all. Then how can we understand this seemingly quite a strange situation? For example, let's think about a certain point, an intermediate point. This is not belonging to the beginning point or the ending point, somewhere around in between. In this case, please try to draw size of your flux with an arrow. Will you draw in this way? Maybe not. Then how about this? Will you draw in this way? Well, maybe not. So maybe you will draw some relatively shorter arrow like this, for example. Then natural question is, between these 2 points, what happens? Yes, more electrons were injected from this space charge region, and now we have less electron. That means that in this part, between these 2 points, something happens. And what is something? Which event happened in this case? The event is quite simple. That is nothing but recombination. We had, for example, 100 electrons comes in and we just walk. However, half of it was just recombined with holes. So now we have to say this way: per unit second we have 100 electrons comes in, and now we have just 50 of it is in this case. Then what happens in between these 2 points? Per unit time we are now losing 50 electrons per unit time. In order to have a recombination of electron corresponding to 50, at the same time we have to have what? We have to have also loss of 50 holes. I mean that without sacrificing 50 holes, we cannot kill our 50 electrons, because they are exchanged 1 to 1. Then yes, from the viewpoint of our balance band, there occurs some events, and our 50 holes are every second or every unit time, 50 holes are just goes away. Then how can we support the steady state? The only way is, okay, if you are losing your holes, then I will just provide this loss of 50 holes into it. Simply speaking, now your anode supply the amount of holes recombined in this quasi-neutral region. That is the form. So simply speaking, although we have reduced electron flux shown here, sorry about that. Although we have reduced electron flux here, that is perfectly compensated by this hole flux. So the sum of this electron flux and hole flux will be a constant all over our quasi-neutral region. So that is an important case. Please note that if we don't consider this kind of recombination process, then actually our electrons and holes do not interact any longer. I mean that because once electrons are injected from n plus region, but if we do not allow the recombination, then that electron will just go until arrive at the another contact without affecting the hole's transport. So therefore, this kind of non-uniformity in our current density only occurs from the interaction between electrons and holes. However, important point is, although in between conduction band and valence band they can change their electrons, but overall, when we consider the overall system of electrons and holes, then current should be conserved. I think that this is quite an important one. Please note that. For example, let's say that we are a small society, isolated from the external world, and now the total amount of money is now fixed. So then let's make some exchange, so make some economics in this small society. Then after that there will be the change of money between persons. However, if we just observe the total amount of money in this small society, then it will be just kept as a constant. Quite similarly, even though electron system and hole system, they can contribute to something, but at everywhere in this device, current should be constant. So simply speaking, we must say that Jn plus Jp at steady state should be a constant. So what is that constant? Right now we have no idea, but anyway we understand that should be a constant. Okay, do you have any question? So I think that in elementary level of semiconductor device course, it introduces a little bit complicated discussion. So usually in nowadays many instructors just consider short diode, because short diode is the really practical one, and consider without considering the exchange of carriers between electrons and holes. But this is a more general description about our system. Okay, so now please have a look at this equation. So please have a look at this equation. Although here we have a certain position corresponding to infinity, and here we have a certain position x sub p, the beginning point of our quasi-neutralism, simply I wanted to say that that should be at any position in our quasi-neutralism, the sum of f sub n, f sub p should be a constant. Once again, then you may say that, oh, Jn, sum of Jn and Jp should be a constant, and Fn and Fp should be constant. That sounds contradictory. However, please note that here Fn, Fp have a different direction, so it is actually corresponding to Jn and Jp. If you don't understand, then please let me know. Well, anyway, so this is a positive Fn, and this is also positive Fp. So that's the way we make certain sign, determine the sign of our fluxes. So everywhere inside this system, the sum of fluxes should be the same. But although we have the condition of a constantness, but in between maybe there is also electron flux and there will be also hole flux. But fortunately, if we go to the anode, it is certain that Fn equal to 0, because this at the time there is no further excessive minority carrier electron, so this electron flux goes away, and following this continuity, then we can say that the sum of these two components is equal to the only hole injection flux from the anode contact. That is written in this part. But please note that although written in a specific selection of positions, but this continuity is generally valid, even not in this quasi p-type region, but that should be also valid for space charge region or quasi-neutral n-type region. So now let me okay, so I think that the watch is okay, we have sufficient time. Okay, so now let's extend our system. Up to now we have considered only quasi-neutral p-type region, but now think about the entire system. Up to now we have considered only this part, but instead of that, now consider also quasi-neutral n-type region and space charge region. Then everywhere we have to have the constantness of sum of Fn and Fp. Of course, please note that Fn is heading this way and Fp is heading the opposite way. So please keep this notation. Then we can identify some important points. Where do we have important points? The beginning point of our quasi-neutral p-type region and the beginning point of our quasi-neutral n-type region. And of course we have two contacts called as cathode and anode. And from cathode there is no hole injection. Cathode, this is for just electron injection, and anode, that is only for hole injection. So in this diagram you can see that actually from cathode we don't have any hole flux, and from this anode contact we don't have any electron flux because they are cathode and anode. And now although we have four different observation points, but from the constantness of our sum of flux, now we can say that sum of this arrow is equal to the sum of these two arrows, and also is equal to these two arrows, and yes, this is the case. So are you happy with this discussion? Yes, they repeatedly say that the quantity should be conserved. However, still we have no idea about what is the exact value of that constant. I mean that sum of something should be a constant, and what is the constant? We have no idea. That is the case. In order to improve this problem, we introduce such kind of observation. Here you may find that there are three arrows corresponding to the electron fluxes, and there are also three different flux arrows corresponding to hole fluxes. But maybe you understand only one of them is colored or filled with red color or blue color, and two of them, they are just left empty inside. So I made this distinction intentionally. This fielded arrow and this fielded arrow, now we know its value. Now we know its value. Really? So the expression for this electron flux at x sub p was given as what? Was given as, yes, this form. Now we know this guy. So quite similarly, we can find the expression for whole flux at the beginning point of our n-type quasi-neutral region. So point is, please, now let's make a really crude approximation. For example, let me just do it for you without any rigor. Let's say that this is 100, for example, and let's say this is just 30. Then my question is, then what is sum of these two, or what is the sum of these two? Can you answer? These values are given 130, but my question is, please calculate the sum of these two numbers, and please calculate these two numbers, and there, of course, there is a condition. Sum of these two numbers should be equal to the sum of these two numbers. It is not determined at all, so please think about this one. If this one is corresponding to, for example, 100, then that will be 30. However, if this one is 자, 이럴 때는 우리가 그렇죠. 그렇죠. 혹시 폴스 알람일 수도 있지만 이럴 때는 우리가 알람에 맞춰가지고 대피를 하는 게 맞겠죠. 네. 자, 잠깐 대피를 하도록 할까요? 그러니까 이걸 끄도록 하고